In 1888, a Russian mathematician named Andrei Kiselev published a textbook on elementary algebra that would remain in print for nearly 140 years. Kiselev was a graduate of St. Petersburg University who studied under elite mathematical minds, but he deliberately walked away from high-level academic research to dedicate his life entirely to middle and high school pedagogy. His writing was so precise that after a revision in 1938, this specific text became the sole officially approved algebra curriculum for tens of millions of students across the Soviet Union. Many modern textbooks attempt to make math accessible by stripping out the difficult logic and handing students simplified formulas. Kiselev took the exact opposite approach, forcing students to construct every concept from scratch. He believed that secondary education required a text combining strict scientific rigor with absolute clarity of exposition. He never skipped a logical step to save time. By refusing to compromise on first principles derivation, he produced a definitive masterpiece of mathematical architecture that outlasted the very empire it was written in. We can see this uncompromising logic clearly if we look at how he handles a seemingly simple problem, adding two common irrational numbers, like the square root of 3 and the square root of 2. Most students are taught to accept these numbers as givens, rounding them off and moving on. But first principles mathematics demands a concrete structural definition for what their sum actually means. If you try to add these using standard arithmetic, the mechanics fail completely. You line up the decimals, but because the sequences never end, there is no rightmost digit. You literally cannot carry the 1. We rely on modern calculators to give us a quick answer, but they only provide an illusion of exactness by truncating the irrationals at 10 or 12 digits. True mathematics requires absolute precision. This creates Kiselev's central challenge early in his second volume. How do you mathematically define an arithmetic operation on numbers that physically cannot be written down in full? To solve this abstract paradox, Kiselev forces the reader to step away from digits entirely and return to the physical, geometric reality of measurement. In Chapter 1, Section 3, he introduces irrational numbers not through algebra, but through the physical measurement of a line segment. This diagram shows a large segment AB measured by a smaller unit CD. It fits 3 times, leaving a remainder, EB. To measure that remainder, we subdivide CD into tenths. If a fractional piece aligns perfectly with EB, we get a finite decimal. Segments that eventually find a perfect common fractional measure, no matter how tiny we have to slice the unit, are defined as commensurable. But geometry guarantees the existence of incommensurable segments, a physical reality where no fractional unit, even if we divide it into a trillion pieces, will ever perfectly align with the remainder. If we zoom infinitely into the gap between the segment ends, they endlessly slide past one another. This misalignment births the infinite non-periodic decimal. An irrational number is a geometric certainty. Because it represents a real physical length that cannot be captured by finite fractions, it demands an entirely new arithmetic framework. To perform operations on these lengths, Kiselev requires the student to define an irrational number as an infinitely shrinking boundary between two known rational values.
We can see this clearly by extracting the cube root of 2. This number line illustrates his exact terms. We establish a lower bound, or the approximate value with a deficiency, at 1.0. We place an upper bound, the approximate value with an excess, at 2.0. We then test the tenths place. Cubing 1.2 gives 1.728. That is smaller than 2, so our lower bound deficiency value slides up to 1.2. Next, we cube 1.3, yielding 2.197. That is larger than 2, so our upper bound excess value drops down. We have successfully trapped the true value of the cube root of 2 within a 0.1 margin. Moving to the hundreds place tightens the trap further. Testing 1.25 yields a deficiency, and 1.26 yields an excess. The brackets snap closer together. Because the exact decimal sequence can never be fully written, Kiselev redefines the number itself as this active shrinking interval. He replaces the static digits with a dynamic mechanical trap. With this trap established, we can finally solve the paradox of adding two infinite irrationals, alpha and beta.
Kiselev states that finding their sum means finding a unique third number, gamma, that satisfies two strict inequalities at the exact same time. This table lays out his first condition. Gamma must always be larger than the sum of any of their deficiency values. Adding the 0.1 precision bounds of 1.7 and 1.4 yields a floor of 3.1. The second condition demands that gamma must be permanently smaller than the sum of any of their excess values. Adding 1.8 and 1.5 gives a ceiling of 3.3. As we increase the precision of the input numbers, we mechanically force the resulting sum into a tighter and tighter interval. Expanding to 4 decimal places shrinks the gap to a microscopic margin between 3.1462 and 3.1464. Translating this data back to the number line reveals a master boundary. The left and right brackets march toward each other with every added decimal place, perfectly converging on a central point. By replacing the impossible task of adding infinite digits with the flawless logic of converging limits, Kiselev mathematically bypasses the barrier of the infinite decimal. Up to this point in their education, students have relied on discrete, finite algebraic rules, like expanding polynomials. Now they are executing continuous bounding logic. By framing irrational operations through deficiency and excess, Kiselev is teaching the foundational mechanics of university-level real analysis to secondary students. These shrinking boundaries are rigorous concepts known in higher mathematics as Cauchy sequences and Dedekind cuts, disguised here as basic decimal arithmetic. He meticulously sets this up in Chapter 1 through careful work on identical transformations, perfectly pre-computing the logic the student will need for Chapter 5's formal dive into limits. At no point is the reader asked to take a leap of faith. The continuous infinite is built entirely and safely using the concrete tools of the discrete finite. The sheer historical footprint of Kiselev's algebra reflects the success of this method. This text shaped the mathematical intuition of generations of engineers, physicists, and scientists. Its longevity proves that true mathematical rigor does not alienate students. It grounds them in absolute certainty. By refusing to gloss over the physical reality of the infinite, Kiselev created the definitive architecture for understanding mathematics.